Test 1 2. Test 1 2. Test 1 2. Testing 1 2. Test 1 2.
Professor Gareth Howells, the speaker for today. And I would like to welcome the Vice Chancellor of UNIMI, Mr. Eli, and the students from UNIMI and all the other unis. Thank you for coming today. To start off the event, I would like to go through a bit about Professor. So, he is a global expert in cybersecurity, AI, Chief Technical Officer in the digital security with his identity management with 35 plus research and 240 plus papers. I want everyone to be paying full attention because this is a very valuable lecture to take knowledge from, because we are all taking text one way or another, so sorry. Now, without further ado, I'm going to invite Professor Salvani, our lecturer, and after I'll pass it on to the professor to give his lecture. Thank you very much.
Thank you, our MC today, Prof. Gareth. Thank you for coming. So Assalamualaikum and very good afternoon. So we are very fortunate here to have Prof. Howells from Essex in the United Kingdom. Especially come here not only for UNIMI, maybe you have other activities, but to deliver lecture something on the AI. So as you know, every day AI you will have new things, okay, every day. So now we can hear from the expert about the AI. So I am also very fortunate just to inform Prof. Howells that we also in Malaysia, we have the AI roadmap, and I am one of the team who developed the AI roadmap 2021 to 2025, and at the moment, 85% what is the strategic planning in the AI roadmap has been achieved. So one of it is like National AI Office we have here in Malaysia, and another the more critical one is talent. So talent development is still not enough, and when we talk AI, that is also cybersecurity. Okay, so that is very important. That's why we go together. Cybersecurity, AI is very important areas now, and still insufficient number of talents in Malaysia. I think it's not only Malaysia, maybe for the whole world. Okay, so and also thank you for all the students. Maybe not from UNIMI, maybe some of you from other institutions in BAC, and also we also have online with the students from Mauritius. I don't know whether they are in the stream or not. They're already in the stream. So these are our students doing our franchise programs in Mauritius. Okay, I think I will give this mic to Prof to deliver your speech. Thank you very much.
Okay, thank you very much for that introduction. I think what it sums up that biography is I'm very old and I've been around a long time. And I've done all these different things, and we can debate whether or not how useful they are, but we'll have a think. What I want to do this afternoon is essentially just give you an insight into how we tend to teach at the University of Essex, how we try to get students engaged in the teaching, and to give you an overview of computability and AI, and how we really tend to emphasize how important it is to understand the low-level details, the functioning of how things work, rather than just think about things at a high level and being able to use them as tools, because you can follow a set of instructions and put things together. But if you can understand the fundamental details, this gives you another tool about how you can use your lives, how you can be able to exploit these bits of technology. Just to prove I'm very old, there's a photograph of me. So that's an awful photograph, I know. And it has uses if you want to scare away people you don't want to come to your house. You can put that on the front door and they'll never knock the door. There's a story behind that. We had a photographer who really didn't like the way I parked my car in front of his in the car park, and they put these things in there. There are some more attractive colleagues. These are some of my colleagues, just to prove we're not all too bad. So these are 3 other colleagues in computer science and cybersecurity at Essex that work with me. Right, okay, so what I want to do is explore a little bit about computability first. And really maybe ask you a set of questions and see if you can work out some of these answers. Just to go through them, how many people believe the first statement that's written there? So in theory, we can perform all tasks with computers. And if you say yes, I'm going to ask you to prove it, give you some problems to do. Nobody goes for that? What about the second one? You're saying, well, yeah, obviously they don't do everything at the moment, but look at the way things are advancing. Look at what you can do with generative AI. It's only a matter of time till everything else happens. So you're all going to go for this third option. You're a bit cynical that there are some things which you can't do. And so we're always going to need people to help us out. Right, let's look at a simple problem. Now, it's a very simple problem. One of the things that happens when we write programs is that we make mistakes. In fact, there's a theorem that says you always make mistakes if you run a non-trivial program. Even if you use the generative AI to generate them, you still got to make sure it does what you want it to do. It'd be rather useful if we had an automated way of testing it. So you just send it to this testing system. It'll say, yeah, your program works. Or, no, it doesn't. This is where it fails. Let's step back a little bit from that. I'll make it a slightly simpler problem, because it sounds complicated to start with. Let's see if we can have a program where it just tells us whether or not, if we set our program running, whether it'll stop or not stop. So if you got a little calculator and you type in 2 + 2 and it says 5, okay, it's the wrong answer, but at least it stopped and given you an answer. If you type 2 + 2 and it gives you an error message, it stopped, wrong answer, but still an answer. Type 2 + 2 and it goes into a loop and never comes back to you, then it's disappeared and we're in this particular loop. So what I want to do is think of a program just to test for that case. So if it says it doesn't hold, we still don't know if it's the right answer, but at least we know if it doesn't hold. And I've written it out in this slightly unnecessarily complicated way, just to try and, because I like using variables and meaningless letters on the screen. We can say that we've got our program, this is the thing we've written, P, and it's going to apply to some data D. Now, P could be anything, could be a calculator, could be a virtual reality game, could be something that controls traffic lights or flies a plane. The data is what it executes on. So a calculator, 2 + 2, virtual reality game, details of your character, what it could do, how many powers you've got, all these different things. Traffic control system, what planes are supposed to go where. That's the data. So abstractly, there's no difference. Yeah? So we're just looking at a very general case. We're going to set P running on this particular data D. We're going to ask the question, does P halt on data D? Right, let's first of all be happy that that question has an answer. And that answer is just yes or no. So P executing on D is either going to stop or it's not going to stop. So the question's going to answer, will it stop, yes or no? Anybody think of a third option? Nobody ever thinks of a third option. You could do something, come up with a really abstract idea. Question, and it's got an answer. Right, let's look at how this thing functions. That is a diagram that just says what I've just said on the previous slide. So we've got our little program, we'll call it halt tester. It takes as input the source code of your program, and it takes as input the data you want to execute on your program, and it outputs an answer, yes, it halts, or no, it doesn't. So as I said, yes could be an error message, yes could be anything, gibberish, but it stops, it comes up there, and it's finished executing. So that's just the action that we said on the previous slide. Now, the source code P is just itself data. It'll be in a file on your machine somewhere. It's just a series of zeros and ones making up the code. Yeah? So we could, if we want to, feed that source code into P as data. You could say that's a pretty pointless thing to do. If it's a calculator, it wants to see instructions like 2 plus 2, and it's going to feed in this gibberish. What you'd probably expect in most cases is it gives you a nice error message saying, error, why are you putting this nonsense into me? Give me something sensible. That's the correct answer in that case, so that's fine. Be happy that this is theoretically possible, because the source code is just zeros and ones. You could feed it in to the program. So nothing impossible there. Nothing underneath has changed. It just says, if I do this stupid thing, will this program stop or will it not stop? Same question. Okay. I'm going to take my program now, halt tester, and I'm going to have a look at the code that makes it up and find the bit that prints the answer, yes, the program stops. So I've got P and D coming in, yes, P and D stops. I'm going to replace it with something that goes into an infinite loop. Now I can always do this, yes. Whatever language you might say printf, the program stops. I'm going to get rid of it and replace it with something like while true or while any condition x equals x, something which will never be false. So if I say while true, that's the end of it. It'll never never exit that loop. So it stays in that infinite loop forever, i.e. this program is going to go into an infinite loop in the condition. So I'm going to ask P applied to its own source code as data. Now, my program, funny, will only exit if PP goes into an infinite loop. So does it stop? No, it'll stop. Otherwise, my program goes into an infinite loop. So I can make things a lot worse here. Right. Halt tester, or this amended form funny, is just a program. It's just another code. So I can ask the question of itself. It's just a program. And we said for any P, this is the question. In the same way as if one of you was tasked with knowing everybody else's name in the room, I could ask that person, what's this person's name? I can also ask that person, what's your name? It's the same task. You're just one of the people. So why can't you apply it to yourself? So there's no reason not to be able to ask the question of yourself. So you can ask it to itself. The only way this can exit, let's say, no, is if this is in an infinite loop. And the only way it can get it into an infinite loop, because the only bit I changed was the while statement. The only way it can go into an infinite loop if this is false. i.e., funny applied to itself can only stop and print an answer if it doesn't stop. But the only way it cannot stop is if it does. Happy with this now? So it stops if it does and does if it doesn't. Well, it's looping around and around. Okay. So you're going to have a nice quiet lecture now, and someone's given a little snooze in the back, and some idiot is standing in front of you talking gibberish. Okay, so what's the answer? I can tell you what the answer is. It's far too complicated. My brain's hurting. I've been driven around the city all day. Does anybody actually not see any problem here? Okay, at least you can see that there is something, an issue that we want to deal with. Anybody a bit suspicious at the way I said it? Yeah, it's a bit like when you go into a little conjurer magician. They want you to pick a card, any card. You always pick the one they want to. You don't quite see how they do it, but you know it's just a trick, yeah? The old rabbit from the hat and all this stuff. You know it's just a trick, even if you can't see it. Does anyone think that? And if I spoke properly and didn't rub it on at 100 miles an hour, you'd have a chance of working it out. Yeah. Does anybody think that then? You must be in that situation. The truth is, the only thing is that the program funny, and notice I didn't show you the source code of program funny, doesn't exist and cannot exist. But program funny is just a logical extension of halt tester. I went into halt tester, found the print statement and replaced it by while true. I could do that for any piece of code. The only reason I can't do it is that that statement mustn't exist. It can't be in there in the first place. So we have to conclude that that program halt tester cannot exist. Now let's go back and think about what I've just said. I haven't said there is a problem that doesn't have answers. I haven't asked the question, what's the meaning of life, and we can debate what all this is. So I think at some meta level, I think, well, it doesn't have an answer. We could debate it. I just asked, does this program stop on its data? That question has an answer. Remember from the first slide, it's got an answer, yes and no, and nobody put their hand up and said they can find a third option. So a simple question which has an answer, nevertheless, no method for finding that answer can exist. And this came in the 1930s and caused a major problem because it's so counterintuitive. You sort of feel that if a question has got an answer, there should be some method for finding out what that answer is. But in the case of halt tester, there isn't. Now, just to be clear, it applies to the general case. It has to apply to all problems. You can do it for specific cases. But in general, you can't do it. And actually, you can think, well, so what are we doing? Who cares whether you want a program to stop or not stop? I can do sensor. I can play my games on my PlayStations or whatever. What do I care whether it stops? There are lots of other things it goes through, and there are two examples that you should be able to see. If a program, you can't work out if it stops or not stops. We can't work out if it halts on all possible inputs. And more interestingly, if you can't work out if two things are stop or not stop, we can't work out if 2 bits of code actually do the same thing. That might be useful. Say, this person's written a piece of code, that person has. Can we compare them to find out if they're the same? You can't do that. So we'll find that in a moment, that it actually goes far further than that. But just before that, did you understand all that? No. Does anybody actually, did anyone understand? I've had people put their hands up to this, not many. Nobody understands that. Nobody's not clear. Anybody sort of get the idea that everybody said that actually. Computers can't do anything. But didn't understand the argument because it was far too quick. Yes, I mean, you can't expect to understand something like that. So yeah, if you had more time, you can probably work out what this person was doing. If you've got the conjurer on the stage and the thing, you can work out how the trick's done eventually, where the words are and whatever. Is anybody now getting a bit fed up? We're only a few minutes into this, and he's already given me something that's got a migraine. And hardly even got going. There's a lot more to come. I mentioned the word algorithm. So what exactly are algorithms? Algorithms are sequences of instructions to perform a task. Yes, all computer programs are algorithms, but so are other things. Recipes for cooking, knitting patterns, there are algorithms as well. And we can express them in different ways. If I told you how to get from here to the center of Kuala Lumpur, I could give you a set of instructions: go out that door, go down outside, turn whatever direction it is, and follow those, you'd get there. Or I could also say, just get the GPS on your phone, press in Kuala Lumpur Center, and that's a different set of instructions. It's a very different set of instructions, but they're different ways of achieving the task. What we've tended to find is that any way you define algorithms tend to come out to be the same. And there are things up here called the lambda calculus and Turing machines that actually look very, very different. Lambda calculus are abstract function definitions. Turing machines are these strange little things called quintuples. They don't look anything like each other, but actually they define exactly the same thing. If you can write an algorithm, you can write it in the lambda calculus, you can write it in Turing machine quintuples. If there's no algorithm that exists, like the halting problem, you can't. So yeah, it's quite straightforward, yeah? Algorithms are a sequence of instructions to perform a task. Right, let's look at an algorithm, shall we? How to get to the moon. Does anybody believe no one's been to the moon? Does anybody think it was all faked in the desert and one of Donald Trump's fake news parts? Okay, so we all think everyone has been to the moon. Right, okay. So it's possible to go to the moon. This is how you can do it. This is how you start. So what do you do next? Find a nice place. Now, it's quite difficult to do this. You need to be quite fit. So don't just go outside and try it yourself. You need to get quite fit to do it. So you need to do warm-up exercises. And you jump upwards, and you land on the moon. Okay, don't need all these rockets and things. Right, so here's the contention. I'm saying that's an algorithm. It's a sequence of tasks. And I'm saying if you do all these tasks, you achieve the aim, which is to get to the moon. Well, that's an algorithm. Is it? There's a question. Oh, there's got people going quiet. Is it an algorithm? Who thinks it is? Yeah, you think that's a sensible way of getting to the moon? Yes. Okay. Maybe not trust you to even getting coffee might be a bit dangerous task to give you if you do things like that. So yeah, so some people think it's an algorithm. Who doesn't think it's an algorithm? Oh, nobody thinks it's not an algorithm. That's an interesting one. Who is suspicious that one of those 5 tasks is more difficult than the other 4? It's almost impossible to buy a decent pair of shoes these days, isn't it? We're a little bit suspicious of that one. Anybody really getting fed up of all this? Yes, it's getting ridiculous, isn't it? You just want to sit there and just have to think about these things. Yes, in a sense, it's an algorithm. It's a sequence of operations to perform a task. It's not like the halting problem, halt tester. Notice I didn't show you an algorithm for that, even with silly instructions in it. It just didn't do. But it's not feasible to execute that algorithm. It's subtly different from the first one. And infeasible problems are generally things that are actually quite important. We've got things like factorizing large integers, or very large integers. If you could do that, you could break much of the security on the internet. You'd be able to create false certificates. You'd break into people's bank accounts, spend their money. etc. There are algorithms for factorizing large integers. But the ones we know of will take billions of years to execute. So you're not too worried about me breaking into your bank account this evening, because your use of it will have probably passed by the time it happens. So it's actually different. It's an infeasible problem. And you say in a practical sense, we still can't do it. We can't get to the moon by doing it that way. But it's different from the halting problem. So we've got two different things here. We've got computable problems which are infeasible and non-computable problems. Now, interestingly, how can we quantify how many of these there are and how many we can do, and what are the relative sizes of them? Because we said, well, halting problem doesn't occur that often. Well, actually, there's many, many problems are non-computable. Now, it's difficult to quantify them because there are infinities here. There's an infinite number of computable problems, an infinite number of things we can do, an infinite number of things we can't do. So how can you say one's bigger than the other? Well, you can in one sense, in the same way as we would say there are more real numbers than integers. For integers, you go up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you can carry on going forever. And actually, if you go 0, 1, minus 1, you just keep on going forever. There's an infinite number of them, but you tend to say there are more real numbers, 1.1, 1.2, 1.25, simply because, well, nothing else, all integers are real numbers, and there's other things which are not. So you just sort of say there's more of them. And in the same way, you can say there are more non-computable problems. An idea by saying here, if you picked any point in there, you could pick an arbitrary problem. Hitting one where an algorithm exists would be approximately that size, to give you an idea. And the chances of you hitting an algorithm which would execute feasibly computing one is a lot smaller. So actually there's a lot of different things here we can't do. Even if you try to do it into ChatGPT, you can't do it. You're going to do that now, aren't you? You're going to see, give me an answer to this thing and see what it says. What I want to do now is, having told you all this, is give you an overview of how we teach some of the details of artificial intelligence. Because I said at the beginning, what we want to do is give you an understanding of the details for how systems work and how they execute. So you can understand at the low level what things are happening. And if nothing else, give you a clear understanding of what's going on. Because it's very easy to type things into generative AI and think, well, this is the answer to everything, I can do everything. Actually, it's controlling how it was trained and how it was functioning is how that happens. And obviously, I'm a bit pushed for time, so doing it all is a bit of a strain. But I want to show you how one part of one network works. So rather than giving you an overview of the whole network, just focus on one particular part. And this is an abstract part of a convolutional neural network. And this is what they look like. Over here at the end is this dense connected section. You've got inputs here, zeros and ones, and it multiplies them by weights. And multiple inputs are summed in this neuron. It sends another output, depending on the activation function of it, what the number is likely to be. And the big thing about them, an algorithm that was worked out, actually just published in 1985, actually came to light in 1974, which we found out later. It's an algorithm for training this, actually automatically changing the weights, so we don't have to manually set them. And what it does is show you patterns like cars, buses, trucks. And if it produces by chance the right answer, you don't do anything, but if it doesn't, so it says truck, you calculate the error, how these things are changed, and you change these weights subtly so that the next time it's more likely to say car, and you show them lots of these examples. And theoretically, that's fine. The problem is that the inputs are really very general statements. If they're images, they're going to be the pixel parts of the image, and it'll take a long time to work out the components. So there's a red blob here, a green blob here, a blue blob here. It's got to work out somehow what these particular blobs are. Whereas if you have something in front of it that says, this is a car, that's a bus, that's a lorry, then, well these four are about, this is a road. It's got things, you're going to come to that conclusion far more quickly if they've got these little labels on them, rather than it's just abstract images. So what a convolutional neural network does is put at the front of this network a set of filters. And these filters look for component parts of an image. And one of the things it tends to look for, where it starts off at the first layer, just by looking for very simple things like horizontal lines, straight lines, diagonal lines. Then you can feed that in and build up a more complex image. So with horizontal, you can suddenly see shapes, triangles, squares, rectangles. And you can feed it forward again, and you can start as these shapes are more complex. So it might be three-dimensional. You might be able to put low-level an image, or as a car, as a tree, there's a bus. And then you can feed it into one of these networks, and it comes up with a meaning. Incidentally, generative AI, recognizing things, it just tells you what comes next. It's the big idea of that. I'll talk a little bit about that in a bit. But it's how these filters work, what the low-level operation is. Because you see, okay, there's something on the front which picks out horizontal lines. Well, how does it pick out horizontal lines at the low level? So this is how it does it. I said, I'm doing this to show you that we teach the low-level details here, so you can do it. So you've got these little things called filters, which look at blocks in the input image. And we're going to take very simple image to work on. So I've just got binary image. Each of the picture elements is a 0 or 1, so it's a black and white. It's not even grayscale. It's a black and white image with not many pixels, and it's deliberately chosen to have a horizontal line at the top left, a diagonal line at the top right, nothing at the bottom left, and a horizontal line at the bottom right. But obviously, a more complex image would have different things. And as usual with neural networks, they do very large numbers of neurons. You don't want to go through the calculations unless you suffer from insomnia, which is very good. You can work through these things. Got insomnia, you work through these lecture notes, and I guarantee it'll work. These are how filters for doing that actually work. And notice they've just got numbers. It doesn't have to be 3 by 3, by the way. That's just a size of a window. So each different filter is a small pattern. What you do is apply it to different blocks. So you can apply it to, say, those 9 picture elements. And what it does is multiply each one times the corresponding part of the filter. So it does 0 times -1, the top left 0, then 0 times -2, then 0 times -1, which like being a first day of primary school, isn't it? So what that comes to? It comes to 0. Then you've got 1 times 0, 1 times 0, 1 times 0, still 0. What happens at the bottom? You've got 1 times 1, plus 1 times 2, plus 1 times 1, 4. God. That's a really tediously boring low-level calculation, isn't it? But nevertheless, it's a number, and the size of that number indicates how big a horizontal line is. Then it shifts. How much it shifts you can control. So if you start looking at these parameters when you set them up, and it asks you what the stride is, that's what it's talking about, how big it scans across. Understanding what the parameters do is fundamental. So many people build these networks and they just change these things at random until it does something sensible. 1 times -1, 1 plus 1 times 2. So we got -1 plus 1 plus 2. So it results in 2. And this is how it scans along. So you've got 4, 2. That's something which is far less of an image there. -1, a bit of a transition, not really much one way. Then that's an interesting one. That's a diagonal line. And the question is it a horizontal line? Where it's 1 times -1, 1 times 0, and 1 times 1. So -1 plus 1 is 0. So no, it's not a horizontal line. But it's not magic. It's just doing these little strides across. And it keeps going now. -4 just going the other way, positive to negative. I'm sure you can work it out. Let's go down to the bottom right. See what I mean? You could spend ages, if you suffer from insomnia, you go through all these steps. Can you make it to the end without falling asleep? Here we've got 1 times minus 1 and 1 times 1, sorry, 1 times minus 2, 1 times minus 1, 1 times 2, 1 times 1. We've got minus 3 plus 3, and it comes out as 0. Remember, this was looking for horizontal lines. That's all it's doing, that little dot product. Now then, you're probably ahead of the game, can realize if you swing it around, it's going to do the vertical lines. This time, if you apply to the same thing again, this time we go 1 times minus 2, 1 times minus 1, 1 times 2, 1 times 1, minus 3 plus 3 is 0. So that's not a vertical line. It isn't. It's a horizontal line. Next one, well, it's a bit more. It's a bit of a vertical line in there, minus 2. Move it across there, minus 1. That's the diagonal line again. Remember, that was 0 for the horizontal filter, well, it's 0 for the vertical filter as well. You need another filter for diagonal. See, it's pulling out bits. It's telling you where in the image horizontal lines are, where in the vertical lines, and if there aren't either of them, even though there's a lot of clutter in the background, it's disappearing. So you're just seeing abstractly these components. It's removing all the clutter for you inside here. And we can go on here, and it goes all the way down now to the bottom right, where there is a vertical line. 1 times 1, 1 times 2, 1 times 1 is 4, which is a strong indication of a vertical line. So it's saying vertical lines in this part of the image. What typically happens after this is gives you a lot of information, and it's usually far too much because you just want to know if these lines are very short, it doesn't do much. So you can collapse some of this space. And if you want to know what a pooling layer is, you'll see them on the neural networks. This is what they are. There's different sorts of pooling layer. One of the things you do is take the maximum group in any particular area. So this is the vertical one. That's the horizontal one. So typically what you do is group some together, and I'll just group 4 together for such a small example. Biggest number in each group, that's max pooling. I said, which is the biggest number in here? So there it will be 4, there it will be 1, there it's 0, and there it's 2. So it's showing the horizontal lines are in that top left quadrant. Same thing here, 0, 3, 0, 4. So the vertical lines are sort of in this area of the image. Now, as I said, what we've now got is a way of putting shapes together and giving you these channels to deal with, which can now be fed into another layer. Well, as I said, the input, note that all I've done is done these simple multiplications. There's nothing complicated in here. But now I've got inputs that show me in these different sequences, these are where the horizontal lines are, these are where the vertical lines are, these are where the diagonal lines are. You can probably immediately see if you're trying to recognize text, suddenly I've got far more useful data for doing that than just the abstract images to begin with. Especially if you're doing handwriting, because of course there tends to be a lot of error. This is pulling them out. It's saying, oh, this is sort of horizontally-ish, this is sort of vertically-ish. It's far more easier to train them from this. So we get these new images in each of these channels. I can do the same again. As I said, now I've got the inputs, different filters, but this time they're putting together these things, and it can tell you whether they're simple characters, or more generally, the next one up would typically be shapes. There's triangles, squares, rectangles, and how big these particular ones are. You can pick out any particular polygons in the image. And notice all the clutter disappears. You can imagine in an image that the edges of cars and things. Yeah, you could have a car. Now you've effectively got a line drawing of where the car is. You've got the boundaries of it, rather than just a picture with obscured by whatever. And it's far easier to pick them out now and put them together. So that's essentially what's going on here. And we can repeat it as many times as you like. Now you can go in and see how many convolutional layers do you want in this network. This is what it's talking about. This is what it's trying to create. And how many filters do you want? This is what it's trying to create. It wants to know how many of these channels it's going to generate. So now you can think about what you can do a bit more sensibly. So what we would typically do in an exercise is now you'd go away and do a workshop where you change the different filters, change them and see what you can do to recognizing it in different types of images and see how the input images govern how the network needs to be trained to make it work. So this is about the whole convolutional network. Again, you now feed this into the previous backpropagation network, which I haven't got time to go through with you. But actually, there's just little training algorithms, a bit of calculus that works out for the error what these particular values are. And really, none of AI is really more complicated than that. Generative AI, as I said, is rather than recognize what the image is, it's recognizing what comes next. And that's how it creates these things. It's making a prediction about what comes next. And you can govern what it makes for the prediction simply by changing the parameters of the network. So you can govern what it's doing. Most important thing is what it's trained on. If you give it bad examples, it's not going to work sensibly. That's like if you're teaching a child, give it bad examples, it doesn't learn very well. Give it good examples, then it gets the idea and it's able to generalize. And our large language models are doing things like working the dot product of the meaning of words. There's a fairly, actually surprisingly easy algorithm for giving a vector, a range of numbers for representing each words. And we can create meanings for them based on the other meanings of the sentence. A typical example that often gets quoted is the word apple, because apple has two fundamentally different meanings. Apple meaning the name of a tech company and apple meaning a type of fruit are two totally different concepts. So if it occurs in the sentence, you can't just use some default meaning for it. It's the classic example to why learning a machine to learn languages is so difficult. But if you generate the dot product, if you can think of two vectors in here meaning technology and fruit, and another word in the sentence is phone and Apple phone, the word phone is going to multiply the technology meaning, and it has no fruit meaning, so it doesn't multiply the fruit meaning. If it's got a sentence, an apple and a cherry, cherry will multiply the fruit meaning of apple and not have the technology meaning. So you can build it like that. And yes, there's a bit more of the details to it, but that's basically what's going on. That's basically what we're dealing with. And at Essex, this is what we like to do in terms of teaching students. Give them examples of low-level details to get you to understand the abilities of the technology. Because it's not magic, it's just a lot of low-level multiplications. All these generative things are really just scaling up these particular parts and getting the right training examples. So when you ask something, what is the capital of France? When it comes back Paris, then it means that the training examples were good. If you let it train arbitrarily, and this was a major thing in the late 2010s of getting the training right. If you got sentences like, what is the capital of France? She asked. What is the capital of France? He said. The next word is she and he. If that's the only example you're going to train it on is large bit of prose, then you're going to get saying, what's the capital of France? Say, oh, she is the answer, because that's what comes up most often when you do it. So you need to think about how you train it, and how you train it is giving it examples. It's just like anything. Just like your abilities are based on your experiences of life, and if they're good examples and good suggestions, you tend to do very well. If you get poor examples, you can go off and do strange things. You think this is the way to do things, and it isn't the way to do things. So that's what we're trying to build these things into our teaching. So much of my research is to do with device authentication. Many of the projects I give for students are to do with device authentication. They can learn about cryptography, they can learn about the details. My company commercializes this research. You can be involved with that company, you can get involved with other companies that we've got with us. Now, we're computer science and electronic engineering, which means there's a range of things. There's the standard computer science, where we have a large number of options available. Do a lot of project work in each year, and in the final year, there's a large individual project. This means you can focus on some of these in detail, so you could build one of these generative tools. We have focused ones in artificial intelligence, computer games, electronic engineering. So these are the sort of things that we're doing. We don't want to base on student numbers. This is a classic slide I don't really like. When you say teaching facilities available, it doesn't mean anything abstractly. Is it? I could say there are 100 floors of labs that are full of equipment, but if there's hundreds of thousands of students, that means they don't get used to the equipment very much. What we have is the sufficient equipment for the student body that we have. There's the ability to do what you need to do. Because the other thing, yeah, you could have all these computer labs, they're not open most of the time. It's an empty building there, which I would be able to do work on. We give people access to the facilities as well. We also like to pride ourselves on we're accessible. We get known by our first names. We encourage students to come and tell us when their problems occur. And you can say, well, if you've got a very large class, that's not going to work, is it? But actually it does, because usually only a small people have a specific problem, and you can deal with them at that level and bring people forward. So thank you very much for listening to me. Did you want to say anything? No. Do you want to say something, Wait?
It's okay. I'll just take the mic here. All right. Thank you so much for the lectures from Professor Gareth. Yeah, I hope you guys learned something from the session today. I'm just going to share some facts about University of Essex, and in case you are interested to further study with us, you can always University Placement Office to with us, or you can just go to our website to look for further information. So, University of Essex, we actually have 3 campuses in the UK. So the main campus is called Colchester, and this is also the campus where Professor Gareth based in. Okay, so if you are going to study in computer science related programs, then you will also be based in the Colchester campus. So where is Colchester? Colchester is actually located very near to London. It is 45 minutes away from London by train. So it is a young city in the UK. So if you're interested, you can find out more from us. We also have scholarship provided for you guys. So if you are looking forward to go for a postgraduate master program, then you can look for us as well. We have a wide range of the School of Computer Science and Electronic Engineering courses that is available in our campus, like computer science, we have cybersecurity, AI, and so on. So just waiting for you to explore more with us. Thank you so much.
Thank you, everybody.
All right, so we also have some souvenirs to give Unimai. So thank you for having us today. Oh, I also need to take a photo. Okay. Mr. Tilika.
Okay, thank you, Professor Howells, for the very exciting and informative lecture. Now, before we end, okay, yes, we can give him a round of applause once again. So, before we end this lecture, so if you line up uniformly in front.
This is going to be interesting.
Okay? facing.
No, we facing there. Wait, you guys stay. Photographer is there. Maybe, Prof, can you
Sit here.